Hello. Today we'll use SOS version 29 to place a satellite in a geosynchronous equatorial orbit, starting from booster Burnout east of Cape Canaveral, Florida. This mission will use new capabilities that are unique to SOS versions 29 and later. We start this mission beginning at the point where the launch vehicle's rocket has burned out. We'll then enter a circular, low Earth parking orbit for about 2 hours, to allow for equipment checkout before transferring to a circular equatorial orbit. From there, we'll initiate an optimized home and transfer orbit, getting the satellite to the final geosynchronous orbit with orbit period equal to 1 sidereal day. Start by clicking on the File tool from the menu bar and then selecting the default project option. This clears all existing orbits that you may have created. You can also do this using the Alt-D key sequence. Now set the location to Cape Canaveral, Florida. I assume that you already know how to do this, but you can watch me do it as a reminder. Next, go to the Simulation Timespan text box and add 1 day to the simulation. Then press the Tab key and recalculate the orbit. Now click on the Add Satellite button to see the Set Initial Parameters dialog. From there, choose the Burnout to Orbit option. Note that epoch is the same as the simulation start time. Do not change it. Assume that burnout occurs slightly to the east of Cape Canaveral. Use the mouse to click on this Earth location. When you do this, the proper GPS coordinates are placed in the corresponding text boxes. Next, enter 30 kilometers for the burnout altitude and 400 kilometers for the desired parking orbit altitude, pressing the Tab key between each entry. Finally, select 0 for the desired orbit inclination and press the Tab key. Note that the orbit inclination becomes 29 degrees rather than 0. That's because you cannot place a satellite directly into an orbit that has lower inclination than the satellite's initial latitude, and the latitude for Cape Canaveral is slightly less than 29 degrees. Now click on the Set Parameters and Recalculate Orbit button. You should now see a ballistic trajectory that reaches apogee of about 400 kilometers. At this point, SOS has added a rocket burn to achieve a circular orbit. It does this by applying a thrust that gives an acceleration of about 6,953 meters per second squared for 1 second. This is the same as a delta V equal to 6,953 meters per second. You may need to move your camera around Earth to see the details of this maneuver. Next, go to the Satellite Group box and change the satellite image to red ball. Note that the default satellite name is Satellite 1. While in this group box, also uncheck the SkyTrack checkbox. Now go to the Display Group box and change spacecraft size to 3. Also uncheck the following checkboxes: Show Location, Star Labels, Satellite Orbit Steps, Satellite Ground Steps, Moon Orbit Lines, and Moon Orbit Steps. Next, go to the Camera Group box in the Monitoring panel and make the following changes. Looking at to Satellite 1, Viewing from to Not Controlled, and Rotation Point to Satellite 1. Assuming that your simulation time span is set to 1 day and 6 hours, you should now see several orbits with altitude equal to about 400 kilometers. Run the simulation and note that the ground lines are fixed to the surface of Earth, but the orbit lines are fixed in inertial space. Now stop the simulation and return to the beginning. Next, click on the Go To Node button 4 times, moving the satellite from simulation start to the equator about 2 hours and 40 minutes after burnout. This gives us 2 orbits to do hardware checkout before firing the rocket again. Note that the orbit has been drifting because of Earth bulge. While the satellite is at this node over the equator, go to the Satellite 1 group box and click on the Add Delta V button. The Set Delta V dialog will open and default to Earth-centric. Do not change this. In the Delta V calculator group box, type the number 0 in the inclination text box, and then press the Tab key. Next, click on the Set Required Inclination button. Finally, click on the Use and Recalculate button to return to the simulation panel. You should now see the satellite in a circular low Earth equatorial orbit. The most efficient way to transfer from an orbit at one altitude to an orbit at another altitude is to use a Hohmann transfer orbit. First, we'll do a rocket burn to enter an elliptical orbit, assuming that our current position is perigee of this new transfer orbit. When we arrive at apogee of this transfer orbit, we'll do another burn to enter a circular orbit. If the apogee for this transfer orbit is 42,164 kilometers from the center of Earth, then our satellite will have an orbital period equal to 1 sidereal day, appearing stationary above Earth. Now go to simulation time equal to 3 hours and 15 minutes. If the timing for our first burn from low Earth orbit is correct, we can place the satellite over any longitudinal coordinate we want. There is a large ring of these satellites currently in orbit around Earth, serving communications, telecommunications, and weather observation purposes. Next, click on the Add Delta V button. When the Delta V calculator dialog appears, note the elliptical orbit option. To make it easy for you, we've included a GSO button that places 42,164 kilometers in the apogee text box for you. Click on that button now. Next, click on the Set Required Apogee for Elliptical Orbit button. SOS uses standard equations to calculate the delta V required to get to the desired apogee radius. However, this calculation does not account for lunar gravity, solar gravity, and Earth bulge, which can affect the satellite's trajectory. Our final apogee will be close to our desired radius, but not exact. Next, click on the button below this to refine the calculated delta V and get a more exact final apogee. This value is refined using trial and error. Finally, click on the Use and Recalculate button to close this dialog and return to the simulation panel. You should now see your elliptical transfer orbit. Change the size of the spacecraft to 30 so you can more easily see it. Now click on the Go to Apogee button until the spacecraft is at apogee of this new elliptical orbit. The distance from the spacecraft to the center of Earth should now be 42,164 kilometers. Now click on the Add Delta V button again. From this apogee position, we want to enter a circular orbit. Therefore, in the Delta V calculator dialog, click on the Circularize Orbit button and then the Use and Recalculate button. The spacecraft is now in geosynchronous orbit, but only a portion of that orbit can be seen. Run the simulation while viewing the More Info and Events panel. Note that the orbit radius is very exact, and the period is 1 sidereal day as it should be. Also, verify that the satellite settles over a particular longitude. To choose your own final longitude, you must change the timing for the initial Hohmann transfer burn accordingly. Note that each rocket burn, measured as a change in velocity or acceleration, is recorded for you. You can use this value in the rocket equation, along with satellite mass, to calculate the rocket fuel mass required. Thank you for watching this video. If you found it useful, give it a like and consider subscribing to the channel. We will be producing new content in the future. If you want to be notified when new videos are added, click on the notification bell. We need your feedback, so please leave a comment in the comments section. Goodbye.